Hello everyone and welcome to 9th lecture of Digital Image Processing of Remote Sensing Data course. And I have divided image enhancement techniques in two major sections. And first one we will discuss in this lecture, and the technique 2 we will be discussing in the next lecture. In this one we will first start with the very quickly how image acquisition or data acquisition from remote sensing satellite is done, and then we will proceed with the first very simple image processing techniques. So once the data is acquired, that acquisition, then image processing starts, and the ultimate aim may be to feature extraction, that is through classification of different techniques, and then image classification. And finally, we go for, after classification, we may go for the accuracy assessment to check how our classification how accurate it is with the real thing. Data acquisition, you require a satellite earth station which is on the ground, on the surface of the earth, a rotating antenna or tracking antenna. This is the example of a NOAA AVHRR satellite station at IIT Roorkee at Department of Earth Sciences, and since October 2002 we have been running this earth station. So this is the external component of the earth station which one is seeing. There are two, one is antenna, another antenna is GPS antenna, which is a tiny one which one can see here very clearly. The purpose here to keep track of timings and the location of the earth station, so that because it is based on the prediction of the satellite orbits, and therefore these two things are required very accurately for the accurate data acquisition. And the second component, that is the internal component of earth station, is inside, which is simply a PC based, depending on type of satellite, the data. But nowadays it has become so simple that you can have a simple desktop computer and a receiver, which is also shown in a large form, and there is a software which controls everything. So using such a setup, data is acquired. For other satellites the setup might be a little different, but in principle it will have two components. One is external antenna, tracking antenna, and the second component, a computer and a receiver, so which receives and computer records the data on the hard disk for further processing. Each satellite will have its own footprint, and this is the footprint of NOAA AVHRR relative to our earth station IITR satellite earth station, which in short IITR says, which is located here, and it's a inverted cone, base of inverted cone plotted on the map of the Southeast Asia, and which covers a very large area. So 3000 kilometer radius circle. That means anywhere if satellite is overpassing, like from here to here, or maybe northbound satellite may be passing over, orbiting from here to here, the data can still be acquired. It is not necessary that it should overpass over IITR says. And for all solar orbiting or polar orbiting satellites, such requirements are there, and I am not talking about geostationary satellites or some different types of orbits, mainly of these near polar orbit satellites, or also we call sun synchronous satellite. So setup is like this, depending on the resolution. If it is having relatively coarser resolution, then it will cover a very large part of the earth, like in this case entire Himalaya, which is about 3000 kilometer and roughly in that length, which you can see here is in just one scene without any mosaic or any thing. You are seeing the entire Himalaya here. So because it is having a spatial resolution of 1.1 kilometer. Once the resolution improves, instead of having suppose 1.1 kilometer, if it would have a resolution of say 500 meters, then my swath or the width of my scene will reduce maybe roughly half. So it depends basically on the spatial resolution. Swath is completely depending on the spatial resolution. Higher the spatial resolution, smaller the width of the swath, coarser the spatial resolution. Like in case of NOAA-HRR, swath is very big, and a large area and at continental scale can be covered. This is the example because NOAA-HRR is also having thermal channels. So using visible channels, this is the false color composite of Western India and parts of Pakistan, Afghanistan and Iran, and some countries of former Soviet Union are also shown here. Thus almost the same part of the same area has been acquired in the night time of thermal channels. It looks something like X-ray, but these are very useful thermal channels, and because these can be acquired in night time. The data in thermal channel can also be acquired because you don't require the solar energy for data acquisition. Now for the image enhancement, as we have seen that or discussed that a digital image is a two-dimensional matrix, and if you are having multispectral data, like in this example, 4 bands are shown here. That means they will stack together and data will be acquired. In case of like NOAA-HRR example, at a time or almost every time, whenever the data is acquired, the data was acquired in 5 channels. So, but in night time, because you don't have the visible channels, so only far infrared and thermal infrared channels, 3 channels data is required. Otherwise in daytime 5 channel data is acquired of the same area, and this is what exactly shown here for different bands. You can see line are like this, which we address. Columns are from top to bottom, and this is how the data of remote sensing remains in the system. Now once the data is acquired by a satellite earth station, there are various ways of storing the data, and the first one is called BSQ, or band sequential format, in which each line of the data followed immediately by the next line in the same spectral band. That means the data will be stored band by band. That means if we are having say 4 bands, then first band will be stored, then second band, third band and fourth band. I will be discussing 2 more major types of digital data formats, and then we will see what is the advantage with each and disadvantage also. Second one is the BIP, which is the band interleaved by pixel format, that the first pixel of all bands in sequential order followed by the second pixel of all bands, and likewise the entire image is stored. So again, if you are having 4 channel data or 4 bands data, that then the first pixel of first band is stored first pixel of second band, first pixel of third band and first pixel of fourth band, then second pixel of first band, second pixel of second band, second pixel of third band and second pixel of, likewise the data is stored. And the third one is the bill format, which is band interleaved by line format, where for each band a line is stored. So likewise that the first line of first band is stored, then first line of second band, first line of third band and so on and so forth. Now when we see the advantages associated with different kind of these formats, like for example with band sequential format, that is BSQ, good for multispectral data, because all the bands are one after another. And the BIP is good for hyperspectral images, which is now we are talking about 256 images and many more images. So because when we want to retrieve the data, then we don't have to go at the end of the entire data set. So this allows us to retrieve the data only for that part of different band. So if number of bands are there in a sensor, then BIP is much more compared to other two image formats like BSQ and bill format. And band interleaved by line format, good for the images of a moderate number of bands, 20 to 60 rather than 256 in case of hyperspectral. So many image processing, popular image processing softwares have also evolved their own image processing or image formats, and there are some other image formats are also available. So when we will discuss about the data compression techniques, at that time we will also discuss some popular image formats which are used in digital image processing. And this is a further elaboration on this, that the in the your BSQ, this is how band 1, band 2, band 3 all are stored, and likewise you are having a bill format. Then in BSQ format it is something like that, and in the BIP format, one after another. And band sequential, which is image band at the time, in other words data of all pixels for band 1 is stored first, then data for all pixels of band 2, and so on and so forth. So when in the BIP the data is similar to BIL, except that data for each pixel is written band by band, and likewise these different systems or different image formats have evolved as per the requirements, and also changing with the time also. Now the next important thing, once the data has been acquired by the satellite, no matter in which format, basic image format you have stored, next thing comes how to improve the quality of image. Why a quality of image is required, as told in the beginning, that is in the introduction video, that once the data is acquired, because the data is being acquired from about 840 kilometer, because the satellites are orbiting around that depth in space, and in between we are having the atmosphere. So atmosphere also deteriorates the quality of image, as well as the there are some other distortions like geometric distortions can also come. Some distortions may come through the problems with the sensors, and once the data on the earth through these data acquisition systems, earth stations, then we process the data and try to improve the quality of the data, as well as bring the geographic coordinates so they can be used on with other data sets, especially on GIS platform. So there are many remote sensing data sets which contain high quality accurate data. Sometimes error or noise is introduced into the remote sensing data. Noise maybe from because of wrong calibrations of sensors, or noise maybe because of some other factors. Now the data may have the problem because of atmosphere which is present within the and between the satellite and the earth, and maybe scattering, atmospheric scattering, absorptions, and clouds may be in between, and to some extent clouds can also be removed, but there are always trade-off while removing the clouds. So that's a different discussion, we will not go in that detail. Then there might be distortions or problems or malfunctioning which may be the random or maybe systematic of remote sensing systems due to the hardware problems, uncalibrated detectors or sensors which are on board of the satellites, and they may be improper pre-processing. Once the data is acquired, then initially some pre-processing is also done on the data. So there, if inaccurate this analog to digital conversion is there, then it may bring the ultimately the poor quality of the data. As we have discussed in case when we have discussed the advantages of studying histogram. So first the step in image processing is to check the image statistics, and that can be done very easily by looking histogram of individual bands. So if I am working on 5 or 8 bands, then I should first study histograms of each band, and depending on the shape of the histogram, how pixel values are distributed, I would then proceed for different image processing techniques. These things I have already discussed in case of when we have discussed the advantages or why to use histograms, and in that discussion we have involved that it is very rare to get normal distribution in the satellite data. Sometimes we get negatively skewed distribution because of maybe some land features may be having high pixel values, maybe like in a desert area or maybe a snow covered areas in a hilly region. You may have a bimodal distribution. This may be in a region like in coastal areas, or where a large water body is there and land part is there. Both will have different properties or different values, pixel values, and therefore they will be distributed completely differently. You may have a positively skewed distribution just opposite to the negative one. Again, uniform distribution is rare only in case if you have acquired the data of a completely snow covered area, and that too is a flat area, or a completely desert terrain where no land features are there, no vegetation, no water bodies are there, and therefore you might get more or less something like this histogram. Anyway, so also one has to look the statistics, and not much complicated one, very simple features one has to go through, like mean, median and mode, how things are distributed, and this will help us to choose the appropriate digital image processing technique to enhance our images for better interpretation. Generally, image processing techniques can be divided in two parts or two sections. One we call pre-processing, and then second is the post-processing. So in pre-processing, create a more accurate representation through geometric corrections, georeferencing techniques which we have discussed in the previous lecture is already there. We know that why the distortions are coming and how to correct them to large extent, and in case whether the data belongs to a high resolution or low resolution, still geometric corrections can be performed. And the requirement in case of very high resolution, high spatial resolution remote sensing data is that our quality of GCPs has to be very high. But otherwise, all types of remote sensing data acquired by polar orbiting these sun synchronous satellites can be corrected using georeferencing techniques which we have already discussed. Radiometric corrections can also be performed, but you require the individual, like if it is a linear array of sensor, then you require the values of individual cells, how CCDs, how they are performing. Generally, radiometric corrections are done by those who acquire the data and supply the data or upload on the internet. So radiometric corrections generally is not done at the end user level. Atmospheric corrections, of course, atmospheric correction may be performed by an end user to improve the quality of image. To some extent, the distortions which are coming because of the presence of atmosphere can be removed easily. There are some sort of brute force enhancement techniques which are very simple and you can remove. But if you there are some models are available. By employing those models, one can remove the atmospheric distortions. And also, in order to remove atmospheric distortions, you require a lot of data of the same time when the data was acquired. And therefore, this removing atmospheric distortions is time consuming. But if it is required for some quantitative analysis of remote sensing data in various applications, which is very much required, then atmospheric corrections can be performed. And also, can it make easier to interpret images using image enhancement technique, which we will be discussing now. An image can be ordered at different levels of corrections and enhancement. We can also, those who supply the data, we can ask them for different levels of corrections and enhancement. They can supply absolutely ready-made data which will have completely good enhancement. All kinds of distortions are removed, a georeference data for just to start and using them for interpretation. Rectifications, that is georeferencing, we have already discussed. So let's go for radiometric corrections. There might be some simple one maybe systematic one, de-stripping and noise removal. And so radiometric correction, these may come because of the performance of different sensors on board or CCDs on a linear scanner. So radiometric correction is a pre-processing method to reconstruct physically calibrated values by correcting the spectral errors and distortions caused by the sensor. So in order to correct, as I have already mentioned few seconds before, that in order to make radiometric corrections, you require the values to which only those who have developed the sensors, tested or calibrated the sensor, they can apply. But the example here is shown about the de-stripping and noise, how it can be removed. And here, if it is systematic errors or systematic noise, which can be removed much easier, but if it is non-systematic, then it becomes very difficult, because pixel by pixel is difficult to correct. But if there is a systematic error, then appropriate algorithms can be developed. There are already some, and these can be employed to remove, like in this example. So this is a system errors which results in a missing or defective data along a scan line, and that has been removed. Drop lines are normally corrected by replacing the line with the pixel values in the above and below and averaging the two, because once you have lost the original data, then there are no ways to recover that data. So how one would recover from neighboring pixels, and this is what it is done in this to remove this stripping effect from the, or bringing this de-stripping technique. This is how it implies. It takes the values from adjacent pixels, average them, and put to the for an incorrect pixel. You might be having this this type of error, that is the speckle noise kind of error, generally occurs in the microwave data, but still, if even in optical data, if it is there, it can be removed. There are definite techniques are available. In this example here, that speckles has been completely removed from the data, and now this processed image looks much better. And then interpretations can be highly reliable. If we make the interpretation on an image which is suffering from noise, then there will be problem. Now atmospheric corrections, because we know that solar radiation is largely unaffected as it travels through vacuum of the space. However, when it interacts with the Earth's atmosphere, it selectively scatters and absorbed. Why selectively? Because in different parts of EM spectrum, the performance or behavior is different, and therefore this word selectively has been used. And both kind of these phenomena will occur, scattering and absorptions, and ultimately these phenomena brings the poor quality in the image, our remote sensing image. So one always try to remove as much as possible or minimize their effects in the images, so our image quality improves for better interpretation. Sometimes some of these two forms of energy loss, we call that atmospheric attenuation. The general aim or goal here is about atmospheric correction is to turn digital brightness value, that is pixel value, recorded by a remote sensing system into the scaled surface reflectance value. It depends on which part of EM spectrum or in which band you are working. And these values can then be compared to use in conjunction with scaled surface reflection values obtained anywhere else on the planet. And this is how these models have developed to remove the atmospheric correction. So the basis of these models are like this. Because as I have mentioned that scattering, absorption, refraction and reflection, all these phenomena are there, and this is the sun is there, this is the satellite is shown, and all these are occurring within this atmosphere within that 100 kilometer. And that creates a lot of problems in our satellite images. These are several ways to atmospherically correct remote sensing data. Some are relatively straightforward, as I told earlier, and we put them as a brute force kind of thing. Some are very complex one, being founded on physical principles and requiring a significant amount of information to function probably. What is that information is the weather data at the time when the data was acquired by the satellite. The corresponding weather data is very much required in order to achieve a very good atmospheric correction. So, and that kind, depending on your requirement, one would collect the data and do that kind of correction. I am showing just one example. This is the image before atmospheric correction, and this is the image, the same image after atmospheric correction. So the distortions which we are coming on the left image were due to the haze, and this is a very common phenomena over large cities like in Delhi or over Beijing. Generally we see there is a haze, and even on the ground we can see. So think that when the satellite is acquiring the data, it has to completely map or incorporate this haze in its data. Now this haze, the presence of haze will reduce the quality of image, and once a image is suffering from that, then interpretation based on these images may be also having a poor quality. So in order to remove this, then atmospheric corrections can be performed like here, and on the right image that haze has been removed, and this after atmospheric correction using the example here is this at core model, and this is there, but there are many various models available depending of location and the availability of the meteorological data. One can go for different kind of models. Image enhancement techniques, modification of an image. This is the definition which we are going through, that the modification of an image is to alter its impact on viewer or interpreter. Ultimately we are going to use image to interpret, go for classifications, use the image, because this is the main purpose of acquiring the remote sensing data. So enhancement are used to make it easier for visual interpretation and inferences. Inferences is very important thing. In the roughly at the end of this course I will be showing some examples where just making interpretations and making inferences, how one can use these remote sensing data for different applications, maybe for groundwater, maybe for earthquakes studies, maybe for fog studies, and so on and so forth. So process of making an image more interpretable for a particular application to attenuate a certain image features for subsequent analysis or image display. That's the main purpose of image enhancement, and this is attempted after image is corrected for distortion. So first atmospheric distortions are removed, geometric distortions are removed, georeferencing is performed, then we go for image enhancement, and may be performed temporarily or permanently. Generally we go for temporarily because we keep original image intact and a new image is saved which is not having all these distortions and having these image enhancement and better quality for image interpretation. So raw image is useful, that is data often populates only a small portion of available range of digital values. So when you display a histogram of a raw image, you would find generally that it is occupying on axis scale, occupying only a small range, and whereas our digital image processing are capable of displaying data. If I am giving example say of 8 bits, then 0 to 255. So that so we can rescale by employing these image enhancement techniques. There are different types of image enhancement techniques. One is based on radiometric enhancement techniques, that is modification of brightness value of each pixel and image data set independently. Point operations, generally this kind of thing is not done, very rare to do it. Spectral enhancement is more common, which is enhancing images by transforming the values of each pixel on a multi-band basis, because not only we will be working on one single band but multi-band using multispectral data. And spatial enhancement, modification of pixel values based on values of surrounding pixels, that is local operations. In case of missing pixel values or some operations like spatial filtering, other things, we use the values which are surrounding a target pixel and then modify the pixel value of the target pixel. So radiometric enhancement, if we discuss, that is the modification of brightness values of each pixel in an image data set independently and brings out contrast in the image. Ultimately, the quality of the image, it looks better for interpretation. Applied separately to each band of data, an enhancement applied to one band may not be appropriate to other bands. This one has to remember in case of one is doing image processing for multispectral data, then this the technique should be performed on individual. The geometric corrections and other things is fine, but these techniques should be performed on this. Contrast enhancement basically falls under the radiometric enhancement. So image enhancement improves interpretability of image by increasing apparent contrast among various features. Contrast manipulations, which is we put them as contrast stretching, contrast enhancement, spatial feature manipulations, which is spatial filtering, edge enhancement, and Fourier analysis, which is not in spatial domain but in frequency domain. But we do the inverse transformation, so we put them in this category, that is spatial feature manipulation. And third one is the multiple image manipulations, that instead of using one band, we use multiple bands. So maybe a technique like band ratioing, which is arithmetic based, principal component more statistical based, and then vegetation indices is again arithmetic. There are various indices have been developed in past depending on the data available, number of bands, and so on and so forth. Why images suffers from low contrast, as I have been discussing, because the individual objects and background that make up the terrain may have a nearly uniform electromagnetic response at the wavelength band of energy that is recorded by remote sensing system. So this if the land part which is being scanned by a sensor having a homogeneity present, maybe a completely forest cover area or a desert area or a snow covered area, then you may have lack of contrast, and that lack of contrast may create problems during interpretation. But if within one image lot of different materials are present, different land features are present, they will have different reflectance or other values, and therefore they will have may have better appearance. So different materials often reflect similar amounts of radiant flux throughout a visible, near or mid-infrared portions of EM spectrum. Cultural factors, for example, people in developing countries use natural building materials, wood, soil in construction of urban areas, and these may also bring low contrast in your image. Further, sensitivity of detectors. If detector means the electronic part of sensors is not good, then that may also be the reason for low contrast. That is, remote sensing system may lack sufficient sensitivity to detect and record the contrast of the terrain. These problems were earlier when we started this civilian remote sensing in 1972. But now things have really improved, and the image quality, spatial resolution, radiometric resolution, all the resolution are improving. So detectors on most sensing systems are designed to record a relatively wide range of scene brightness values, 8 bits 0 to 255, without becoming saturated. But in some cases, very few scenes are composed of brightness values that utilizes the full sensitivity or range of detectors. And if an image is having this kind of occupancy of pixel values completely exhausting, then there is no scope for any further enhancement. Atmospheric scattering may bring the low contrast, that is, scattering of electromagnetic energy by atmosphere can reduce the contrast of a scene, and this effect is most pronounced in shorter wavelengths. So the bands like wideband 1-2 in case of Landsat MSS or Landsat ETM, TM, OLI, these problems may come. Now we come for this contrast enhancement. The first one, the amount of difference between average gray level of an object and that of surrounding. So we put that as a contrast enhancement. The difference in illumination or gray level values of an image, or intuitivity, how vivid or washed out an image appears. ratio of maximum intensity to minimum intensity. Larger the ratio, more easy is to interpret the image. So contrast enhancement, basically maximum gray value divided by minimum gray value. This is the example here. What we are saying, that on the left side you are having original image, on the right side you are having stretched or enhanced image. So the original image has this kind of bimodal distribution. In the histogram, the same histogram has been stretched to the full length which is available for us between 0 to 255, and once we do it, and then we reached this kind of image, which is much better for image enhancement, which is much better for image interpretation. Similarly, before and after effects of this contrast stretching are shown here, and the interpretation may be very difficult, but once the image has been the contrast of the image has been improved by implying a simple image enhancement technique, then our interpretation will definitely improve. There are some other ways of doing this thing. Again, the example is the histogram, where the values are being distributed between 60 to 158, whereas the range available in digital image processing in 8-bit based is between 0 to 25. So we can rescale this thing, and then these values can be stretched. That is why it is called a linear stretch or contrast stretch, because we are redistributing values from between, in this example, between 60 to 158 to 0 to 255. And by bringing this stretch into the distribution of images, ultimately we improve the image and contrast and better interpretation. So contrast enhancements expands the original input value to make use of total range of the sensitivity of display devices, and the density values in a scene are literally pulled further apart, and that is expanded over a greater range. That is why I am using word stretching, and the effect is to increase the visual contrast between two areas of different uniform density, and this enables the analyst to discriminate easily between areas initially having a small difference in the density. So the values difference between two adjacent areas or two adjacent pixels becomes larger, and therefore the contrast improves. There are different types of contrast enhancement, which pixel values in most scenes occupy a small range of values. Raw images generally will have, if you see the histogram, they will occupy a very small part between part which is available between 0 to 255, and this results low display contrast. A contrast enhancement, as mentioned, expands the range of displayed pixel values, not the original one, but the displayed pixel values through LUT, which we have discussed in previous lectures, and increase the image contrast. So there are various types of image contrast. The linear contrast stretch, that the input and output values follow a linear relationship, a minimum to maximum, minimum maximum stretch. We also having percentage stretch, standard deviation stretch, piecewise linear stretch, and sawtooth stretch. Various types of algorithms or various approaches people have developed, but which will fall on this linear contrast. And once you are having linear, then definitely there are non-linear contrast enhancement techniques where input and output data values do not follow the linear relationship. In case of linear, they follow the linear relationship. And non-linear contrast stretch like logarithmic, inverse log, exponential, square root, etc. So first we will take the linear contrast stretch, which are based on linear concept, that a digital number or pixel value in low range of original histogram is assigned to the extreme black, and the value at the high end is assigned to the extreme white, and the rest of the values are distributed in between, and this is simple linear contrast stretch. Remaining pixel values are distributed linearly between these two extremes, an example shown here. And this is how the lookup table is. The transfer functions that the original values were here between, say, 40 to 200. Now this has been stretched between 0 to 255, and this is how the advantage of lookup table, and by which we can achieve linear contrast stress very easily. By expanding the original input values of the image, the total range of sensitivity of the display can be utilized, which is available between 255, and linear contrast enhancement also makes subtle variations within the data more obvious, and these types of enhancements are best applied to remote sensing images with Gaussian or near Gaussian histograms. That means a normal distribution. So if you are having distribution which is near normal or normal, then this is the best technique to employ, which is very simple one, and very quickly one can achieve very good enhancement. So this brings to end of this particular lecture, which is first part of image enhancement. In the next part we would be seeing more linear and enhancement techniques and as well as non-linear enhancement technique. Thank you very much.